Okay, so we're at the point now where we want to do the integral over y. And when you want to integrate the derivative of a delta function, one strategy that will always work for you is to integrate by parts. So let's do that together so that you know how to do that. So this will be an integral d3y, and I'm focusing on the first term now. I'm going to write it as follows: minus I nabla with respect to y dotted into nabla of phi of y comma t times by the delta function. And then there's another term which comes with a different sign, plus I, the Laplacian, so nabla dot nabla onto y, acting on phi, and then multiplied by the delta function. Okay, so let's just talk about this quickly. This term on the previous line is equal to the sum of these two terms that I've just written down. Okay, so let's see why that's the case. Well, look at the first term of the last line. When nabla acts, it can act on two things by the usual product rule for derivatives. It can act on the delta function, and then it gives you the contribution from the line before. Or it can act on the gradient of phi. And if it acts on the gradient of phi, it gives you something new that didn't appear before. What does it give you? It will give you minus I, the Laplacian on phi, times the delta function. But that new term that appears by acting on the gradient of phi exactly cancels against the second term that I've added. Okay, so make sure for yourself that you can see that the red term on the previous line is the sum of the two red terms on the line that I've written here. And then let's take a look at the second term on the second last line. Well, there's just a delta function. That integral is easy to do. It's just going to set x equal to y. So we get minus I m squared phi of x comma t. Now, what did we gain by doing this manipulation? Well, if you take a look at this term sitting over here, this term over here is the divergence. It's a total divergence of something. So that means that this term is a boundary term. So you should be getting very used to neglecting boundary terms by now. Why do we neglect the boundary term? Well, the boundary term lands up being evaluated as a surface term, so something on the surface of the integration domain. And on that surface, at infinity, the field phi itself vanishes. Also, because x is some point that's internal, the delta function would also vanish. So that's two good reasons to drop the boundary term. So the boundary term can be dropped. Good. Now, look at the term that we've got left. Well, that one's pretty easy to evaluate because there's just a delta function. What will the delta function do? It'll set y equal to x. So we'll end up getting I with the Laplacian. Okay. In fact, I don't even need to indicate what we're differentiating with respect to. There's no ambiguity anymore. This is on phi of x and t. And then we've got minus I m squared phi of x comma t. What was this equal to? Well, this was equal to I pi dot. So I'm going to drop the I in front of the pi dot and the I in front of the right-hand side. And then what the Heisenberg equation of motion tells us is pi dot is equal to the Laplacian of phi minus m squared on phi. So that's what the second Heisenberg equation has told us. And remember the first Heisenberg equation, it just told us phi dot was equal to pi. So let's put that one down too. Phi dot is equal to pi. Now, if I take the second Heisenberg equation, I plug it into the first one, then because phi dot is pi, pi dot will be phi dot dot. So phi dot dot will be equal to the Laplacian on phi minus m squared on phi, which we can rearrange to say the second derivative minus the Laplacian plus m squared acting on phi is equal to 0. And this second derivative here, I'm sure you recognize as nothing but d mu plus m squared acting on phi is equal to 0. So this is the equation of motion that our field phi obeys. We've calculated that from the answer that we got from canonical quantization. And this is now an equation for an operator. But this exactly matched the equation of motion that we had before from the theory that we constructed using a set of axioms. In fact, anything you choose to calculate now using the theory that we got from canonical quantization will completely agree with the theory that we constructed before using a set of axioms. The axioms were helpful in teaching us how to think about the theory, but canonical quantization is helpful because it's a recipe. It holds also for interacting field theories. In fact, you can just use canonical quantization as a recipe to quantize any theory that you like. For theories with a local gauge symmetry, you have to be a little bit careful, and canonical quantization needs to be modified a little bit, but we know exactly how the modification works, and at the end of the day, we land up with a recipe with which we can quantize any quantum field theory, whether it's free or interacting. On the other hand, our approach that used a set of axioms worked perfectly well for the free theory, but it would have been hard to guess a suitable set of axioms for the interacting theory. No problem. Now we'll just use canonical quantization, and we can study any quantum field theory that we're interested in. Great.